chapter that you guys haven't heard already before, chapter 13, which is liquids and solids. Most of this information we've already talked about in different contexts in the class, except for a tiny bit of intermolecular forces. All right. Properties of liquids. Very similar to things that you probably already experienced. They have a fixed volume, but they can change their shapes. They flow. They don't compress or expand significantly. However, there are some liquids that do. If you've ever experienced hydraulics, if you have worked on cars, or if you've seen where they take a car and they put it up on those racks in the automobile shops, that's actually liquid hydraulics. A lot of people think that's gas hydraulics. That's liquid hydraulics. So liquids expand and contract a little bit, but not as much as gases do. And they have a much higher density. The next thing we really need to talk about is what we call intermolecular forces, which is very different than intramolecular forces. So let's look at the difference. Intra
What's inside the molecule
versus inter forces. Right? Okay. Intramolecular are things like ionic bonding, meaning you've got a metal plus a nonmetal bonding together. Things like covalent bonding, where you have a nonmetal and a nonmetal. Right? We've already talked about those kind of things, lots. Intermolecular is the forces between molecules. So between the molecules themselves, like water molecules, right? They're positive on this side, they're negative on that side. What sort of forces are in between the actual molecules themselves? So the definition is a little bit different. So intermolecular forces are much different than intramolecular forces. Intra takes a whole lot of energy to change them. Inter, not so much, because it's just like magnets. Like if you took magnets, for example, and I said, all right, polar things are like a magnet. You've got a positive and negative end. So if we look at a polar water molecule, it's like the positive and negative ends. If you have two magnets, and you have the north and the south end of a magnet, if I bring another magnet up next to it, and I put the two south ends together, what's going to happen? What's going to be the force between them? They're going to repel. They're going to push each other apart, right? They're going to push each other apart. If I take that north-south magnet, and I bring another magnet next to it, and I put the north-south in alignment, what's going to happen? They're going to attract to each other. Well, that's sort of like what intermolecular forces are. It's like you've got molecules that are magnetic by virtue of their polarity. So because they're polar, they're attracted to each other. The strength of the intermolecular forces is much less, but we can rank them in order of increasing versus decreasing strength of the intermolecular forces. We'll rank them, and then we'll talk about the different types of intermolecular forces. The top of the box is hydrogen bonding. If you've had any biology courses, you know that hydrogen bonding is apparent in what super important biology concept? 23andMe? Your DNA strands, those are held together by hydrogen bonds. So those are just intermolecular forces between them. So that's the strongest. Then you have polar, you have dipole, or ion dipole. And finally, you have dispersion forces. So these are the weakest. These sometimes can change places depending on what you're talking about, and these are the strongest. So dispersion forces are the weakest. Now, if we look at the types of molecules that these are between, put a red line here. Everything above the red line, this is all solutions of ionic substances. We're still talking about a lot of solutions. Dispersion forces, these are covalent compounds. All right. So the types of intermolecular forces you can have, the forces that are in between the molecules, these are generally ionic substances or polar molecules. Everything above this line has to be a polar molecule or a solution of ionic substance. Below this are non-polar molecules. So that's the types of intermolecular forces that can exist in the different solutions that we're talking about. So a polar molecule is called a dipole. In your textbook, bless you, in your textbook, they have a depiction of something, say for example, if we talked about the water molecule, again, the positive and negative sides of a water molecule, they call it a dipole. And anything that's a dipole, they just put it as a blob with a positive end and a negative end on the blob. It's just another way of depicting. It could be water molecule, it could be ammonia. Remember, ammonia is this funny molecule. It's got 3 hydrogens hooked up to it. It's got a non-bonded pair of electrons on the top of it. So it has a tetrahedral electron geometry, but a trigonal pyramidal molecular geometry, which also makes it polar. So anything that's a dipole is a polar molecule. Something that has a positive and a negative end to it. So these are one more category is dipole molecules. And it's a dipole force that attracts each other that mostly we're going to see in liquids. So for example, if you took water and water, a pure water substance here, I've got 2 water molecules randomly floating around in my solution. That's not a very good one. We'll make another one that has the ears on this side. They're randomly floating around in solution. This is the positive end of each of those water molecules. As the positive ends approach each other, they're going to act like magnets. They're going to push each other away, and they're actually going to turn in such a way, especially at the surface of the liquid, so the little water molecules are kind of spooning. You know when you got your sweetie, you say, oh, let's snuggle, right? We're going to spoon. Water molecules do that in the surface of a liquid. They kind of spoon with the negative sides on one side and the positives on the other, right? It's like the spoon drawer. That's why they call it spooning, right? In the spoon drawer. And that's what causes surface tension. Have you ever done that? Have you ever taken a glass of water, for example, and you poured it all the way full? Here's the top of the glass. And sometimes you can get so full that the water is like a bubble at the top. And isn't that so cool? And it's because of the surface tension of water. If you try to do it with other liquids, say, for example, oil will not do that. Oil won't do that. So the surface tension actually makes the water molecules closer together at the surface. Because if a water molecule, say for example, here's our container, they're closer together at the surface. I got a water molecule here. It's being pulled on all sides, right? From the water molecules around it. The water molecules at the top are only being pulled in a downward direction. So that makes them closer. It makes them stay tighter together in the surface of the liquid. Hydrogen bonding is a special type of intermolecular force that exists only with molecules that have hydrogen bonded to either nitrogen, oxygen, or fluorine. So if we're looking back at the strength of the hydrogen bonding, this is what I just talked about was dipole-dipole interactions here. Dipole-dipole interactions is between polar molecules. Now if we take something that's ion dipole interactions. And we got our polar water. And all of a sudden I'm going to put some NaCl in there. When it dissolves, what does NaCl break up into? NAs and Cls. All right, so we have a positive ion here and a negative ion there. That's what we call ion dipole interactions. Sodium is the ion, water is the dipole. And And what happens is the ion is surrounded by the dipole. So if you look at the strength of the intermolecular forces, dipole-dipole interactions are like water to water or water to ammonia. Ion-dipole interactions are something like you take ionic salt and you put it into water, and that creates the interactions. That's why the boiling point of water is increased whenever you put salt in water. If you've ever cooked and they tell you pasta recipes, and they say if you live at high altitudes, like say for example you live in the Rocky Mountains in Colorado, where water boils only about 92 degrees, that's the hottest that it gets. When you want to get your water hotter, they have you add salt. What that does is the salt molecules, the little ions here, attract the water to it, and it makes it harder. It's like adding more magnets in the water. The more magnets in the water, the harder it's going to hold the water molecules in there, so it has to get hotter to boil the water. So these things can influence the boiling point of solutions. If you want to boil at an even hotter temperature, what would you do? Add more salt. The more salt you add, then you have some really salty pasta, right? The more salt that you add, the higher the temperature is going to get. And that's what we call a colligative property. All right, we're going to stop for today.